stay in the same topic as the previous lecture was, but it will be handled from the practical point of view. I will concentrate on the application of data analytics in power engineering domain. Well, we know that we daily gather and collect and store huge amounts of data, and really the right value comes only in case that you process them and analyze them. And it's true also for the domain of energy. So let's look how data analytics and machine learning methods can support better operation and design of smart grid. A few words about me. I work at the Faculty of Informatics and Information Technologies in Bratislava, as I was introduced, and my field of research is intelligent data analysis and predictive modeling, cluster analysis, anomaly detection, and optimization. Then a short info about Slovakia. As also was said, Slovakia is a little country with 5 million inhabitants only in the heart of Europe, and Bratislava, where our technical university is located, is the capital of Slovakia. And here you can see the building of our faculty. So now come to the topic of the presentation. There are a few themes which I would like to talk about. The first one is what is smart grid, what smart metering data look like, why power load forecasting is important, then something about methods of forecasting which we have researched and which we have experienced, and then what can be optimized in smart grid, which will be the topic, I think, for the next years now. So let's start with smart grid and the evolution of smart grid. So the traditional view of power grid consists of main grid and consumers. Consumers consume the energy, and besides households, we have the factories and SMEs and so on. But with emergence of renewable energy sources, we can see that the smart grid is not anymore centralized, but the distributed sources of energy are there. And also, that means photovoltaic panels and energy, solar wind turbines. And as they are dependent on weather, so and it's not so, it may be unsure, so energy storage systems are needed. So this is another component of smart grid. And as we all know, so plug-in electric vehicles now are in place, so this is another big issue which comes into the whole concept of the smart grid. Well, as the distributed sources are here, so now the communities can join together and form so-called microgrids. That means little communities which can be as independent from the outside grid as possible, and it is now a task to optimize the really operation of microgrid. And this is quite important because it's the new paradigm which emerged, and we have to do something in it. Of course, this is possible only because we have smart meters, which I will talk about, and these are appliances which measure electric energy. Maybe you know it, every 15 minutes or every 30 minutes, and then these data are transmitted and then processed. And this is our task, that we use data analysis to support all these activities. So this was the introduction. Now, what smart metering data look like? Normally we have measurements every 15 minutes. That means we have 96 measurements per day in one household. When we take a small city, not so big as you have in India, but maybe 200,000 people, so it may be around 500 million data, but in 1 month. And when we take 1 year, but in a small region, maybe 500,000 of inhabitants, then you have billions of data, and that means that this is now the characteristic of big data, and we have to handle it in this way. When we look at, moreover, it's infinite data set, because the data are streaming in this manner, yeah? They are streaming as infinite data set. If we look at the time series, which is the characteristic of the power consumption, we see that every consumption can have another shape. For example, the first one is the weekly household energy consumption in Texas, its household. And the second two are administration office in Slovakia. As we can see, during weekends, the administration offices have very little consumption. Yeah? And another thing is that the consumption of households is quite unpredictable. This can be a problem. When we look on the data from the point of view of a whole year, so we can see that there is also some seasonality in the power load consumptions. For example, the first graph is from Tasmania. Usually the consumption is higher during the winter. So in Tasmania we can see the consumption is quite high in June, July and August. In Canada, as we can see, the biggest consumption, the higher values are from December to February. So this is the character of data which we are working with, just to have an imagination what we are talking about. Now we will move a bit further, and we will talk about smart grid problems, which are, for the first thing which I would like to say is the problem of power load forecasting. You know that this is quite interesting problem, because electric energy is very difficult to save. And that's why now we have also batteries, but until lately it was not so easy. And the companies which sell the energy, then are penalized for positive and negative difference in what they plan. So it's really, we talk about big amount of money. So power load forecasting is quite interesting and important issue. Then we have renewable energy resources, which also it is important to know as sure as possible what will be tomorrow's production. So the prediction methods for production of renewable energy sources are also to be developed, because it's an important issue. As I have said, they are dependent on weather, and weather is it is quite unreliable, as we know. So energy storage systems are at hand, and we have to use them, but we have to use them wisely, because it's a difference if we fill it just and empty, or we have some algorithm which is wise and which helps us to use the energy efficiently. And also plug-in electric vehicles now are the part of the whole system, and it will go further for sure. When we take all these aspects into consideration, so we now have the problems which we have to solve, and we see that we need some new methods for microgrid planning and sizing and operation. And that's what is the interest now. The first topic which I want to stop is power load forecasting. And I would like to present you some experience, our approach, methods, and so on, which we have done. So I go to the power load forecasting. As I said, it's really important because even a small improvement in precision can mean high savings. We talk about maybe millions of euros in really big scale. So they can minimize the deviation between produced and consumed energy, and as I said, this is penalized for the distributors, and that means lower regulatory fees for distributions. And it is also important from the technological side, because if we keep grid in a balanced state, so we have lower costs for maintenance for sure, yeah, because the big peaks are not good for the network. So we have worked with short-term power load forecasting. We were in contact with the companies in Slovakia, and it was quite important for them. So now I would like to present you really the approach we took. So we took the time series from the households or from the SMEs or from other smart meters. We summed them up, then we built prediction model, and then we had the forecast, yeah? Because we asked them how they did it before, and they said, well, one man knows it. We didn't use any methods based on analysis of data or something like that. So that was progress for them. Well, how this time series look? We have talked a bit about the data from smart meters, and they are regular in some sense. Yeah, they have some cycles, some seasonality. Because it's regular that during the night you have the lower consumption and so on. But so-called concept drift can also come into place, and that means these can be unexpected changes due to the weather, due to some social events, due to many other events, due to holidays and so on. And we have to take them into consideration with the method. So how we did it? There are in principle two approaches which you can use. And the first is so-called blind. That means you regularly retrain your models and you update them. Yeah? And the second one, but this can be quite demanding. Yeah? And the second one is so-called informed, and it's based on mechanisms which detect the changes. And we have concentrated on this informed adaptation, as I will say later. But now I would like to stop a bit at the prediction models which are used, so you can have the review or overview of methods which are used for those of you who are not acquainted with them. So there are two, you know it, I'm sure, two basic approaches, that is statistical and artificial intelligence approaches. statistical methods are based on solid theoretical foundations, and they are simple, robust, and explainable. Many of artificial intelligence approaches are so-called black box. Neural networks are the example of it. And now the topic in AI is the explainability, because in some areas, for example, in medicine or so, it's very important to explain why the decision is made in this manner. So it's also here that it's black box and it can be disadvantage. Then in statistical methods you have linear relationships in majority, in artificial intelligence also non-linear. They require domain and statistics knowledge, and do not the artificial intelligence, they can deal also without this statistics knowledge. The examples or the main methods are linear regression, time series analysis as ARIMA, exponential smoothing, and so on. So these are the main methods. From AI, you know for sure neural networks, support vector machines, and regression trees. And there are for sure more, but this may be the most used. So it was about the methods, and now we go further, and we can combine the methods into so-called ensemble models. That means you make several models, and then with certain weights you sum them up, and then you have the prediction. This can have many advantages, yeah? But the question is how to get the right weights for the individual models. So, and when we solve it, it's also the good strategy for coping with concept drift. So the first approach which we have tried was the approach based on some measuring of error, of median error, and the result was weighted sum of M-based prediction models forecast, and the weight of each prediction model was based on its past median error, but multiplied with the weight of the previous prediction period. Yeah, the second formula, that means W is multiplied by the median error. And the model has preferred, of course, the models, or the ensemble model preferred the models of the models which had lower prediction error. I will show you later the results and evaluation of this approach. Then another approach, which was more successful, was weighting by biologically inspired algorithms. We tried 3 groups of them. The first one was evolution-based, genetic algorithm, differential evolution. The second was swarm intelligence group of methods. The main methods were PSO, particle swarm optimization, artificial bee colony, and gray wolf optimization. And the third one was a bit strange, so-called biogeography-based optimization. Now we will see the results. Here we have the group of data on which it was evaluated. So we took data where concept drift was present, because it was important for us. It was the focus of our research. And there were several groups of drifts, so-called abrupt drift, incremental drift. You can see the shape, I think that it's self-explaining. And we had also one short abrupt drift, that means the picture on the right side. And the first 3 data were 30 days data, and the last one was 15 days. Now we can see the result. We measure so-called MAPED, that it's the error, mean average percentual error, which is quite popular or known in this area. And we see that biologically inspired algorithm, that means the red ones, and their ABC, artificial bee colony, particle swarm optimization, and gray wolf optimization, outperformed the others. It was really, really good. Even the median-based approach, which we have proposed as the first one, and they were better even as genetic algorithm. And for sure, all these methods were better as base methods, which we can see on the right side of the picture. That means artificial neural networks and so on. And we see also other interesting thing, that statistical methods were better than artificial intelligence methods in this case. Well, so far we have been talking about so-called blind adaptation that I told it in the introduction of this part, that blind adaptation works in the way that every time the new data is coming, for example, once a day, it has been to retrain. But sometimes it's quite demanding, and that's why we have proposed another approach, so-called informed adaptation. And it looks like this, that the errors are diagnosed, so we compute loss estimation, and we update model when we detect the change. So the purpose of change detection module is to decide if the concept drift has occurred or not. So this is really better, because as we see now, the change detected prediction error over last 24 hours exceeded 5%. And what I want to stress, 50% less model updates were required than by blind daily training. So this was really much better. We used double seasonal hold winters exponential smoothing, also because we have seen that statistical methods were really doing the good job, I would say. So this is about this informed adaptation. And then we have tried another approach. Till now we have been working in a little, so-called to say, batch mode, that we had sliding window. It's incremental mode. The best name is to name it incremental mode. But we wanted to try also online mode. That means you process the data in one-by-one fashion, and you don't need to store them. You just forget them. It's really, for streaming data, it can be a great advantage. We used online support vector regression, and the parameters were estimated by PSO. And here we see the results, and we see that online software support vector regression overperformed almost all the methods. Well, there was one which was better, especially random forest, when we divided the models for weekend and for work days. But anyhow, the result was very good, because it was online method where you don't need to store the data. And the last approach I would like to present to you, because we tried quite a lot of approaches, was different from the first ones in that manner, that we didn't sum the time series, but we made the clusters. For sure you know what cluster analysis is. That means you put them in similar groups, and we then make individual prediction model for every cluster, and then we sum the forecast. And it was quite surprising, or maybe not so surprising, but it brought the improvement. So here we can see the comparison of these two approaches, and we see that the clustering brought the improvement quite significant. We have also experimented with time series representation, but I don't go now into the detail into this topic. But you see anyhow that in every case the clustering brought the improvement. And I thought I have a graph here, but it's not here. Okay, we can see it also from these results. So now we move to microgrid optimization. This is a topic which we are now beginning with, so we don't have so much experimental results, but we are working on some applications, on some new methods perhaps. So I would like to present you our endeavors in this field. The problem is, I have said at the beginning of my presentation what microgrid is. Yeah, it's the community which tries to be independent, and the energy sharing is a big topic in microgrid communities, because it's you know, we have today car sharing, we have sharing of many things, and energy sharing is also the topic which will come into place. And it is based on the distributed sources that people have photovoltaic panels on the roofs, but the problem can be that they are not at home when the photovoltaic panel produces the most energy, yeah, because they work during the day. So unused electricity from photovoltaics is returned to grid. Moreover, for example, in Slovakia, you can't sell the energy to the grid. We don't have the legislation. So it's useless, so to say, because you just return the energy to the main grid. So what is it microgrid planning or sizing good for? So you try to utilize the photovoltaic electricity in maximal manner. Then you try to minimal grid deviations, and you try to be as self-sufficient as you can. So these are the goals of optimization of smart grid. Well, you can operate in more ways. So when you want to use the storage, so you can decide if you want to use power from just photovoltaics, from main grids, from energy storage, or you want to charge storage from photovoltaic. You can even charge the storage from main grid, for example, during the night when it is cheap. So these are the manners. And also you can have one shared batteries between or among many households, because it can be more costly, more cost efficient. So the inputs or the aspects you have to take into consideration are load forecast, production forecast, then electricity prices you have to take into consideration. Then, of course, battery parameters, and the output is optimal state of battery during the time period. So the things which I said by the last slide, if you have to charge the battery from photovoltaic, or you have to use the battery during the day, or you have to charge it from the main grid, and so on. There are many aspects which influence the whole operation. Well, the biologically inspired algorithms are also seen to be a good solution to these problems. We are just proposing the solution now, and we use particle swarm optimization, Firefly algorithm. We have done also, I'm nearly at the end of the presentation, some applications, or we developed some algorithms which help the users in calculation of savings or return of investment by storage, electricity energy storage, appliances. So you have also to take aspects into consideration such as localization, if there's sunlight, what radiation you have there normally, then energy price, tariff, state subsidies, consumption, and the profile of the household, of course panel properties, and in energy storage you have aspects like consumption of the household, or profile, production of the household, and battery properties, and then you can do the decisions about if you want to buy the storage, or if you want to buy a photovoltaic panel, and so on. And here are the results which we have got by applying our algorithms. We see that without battery, it's the blue one, and it's higher in every case in import and export from the main grid. And we see that with battery, the export to the main grid is really low. That means in Slovakia it's very good, because, as I said, you can't sell the energy to the grid, so it's much more now. It's much better for the user. Well, we have done some other tools which may be very useful. This one is the user-friendly environment for, so to say, editing the smart grid or microgrid. You can add subcomponents, you can delete subcomponents, and it's a preparation for simulation and monitoring of the smart grid, and we hope it will be very useful. And the nearly last slide, there is some information about other utility apps which we have developed. That means we made some applications to inform consumers about their consumption, explain the electricity bill, because we have seen that people don't understand the bill at all, or it's very hard to motivate them to change their behavior, because they don't know how to lower their cost for energy and so on. Then these apps could recommend, these apps recommend consumers the electricity supplier, motivate them. This is quite difficult part to motivate users to change their behavior and to save the electricity. And well, they have also recommended moving or limiting the consumption of electric appliances. We had also developed some apps for electric vehicle drivers, so they can find the charging station, they can reserve the time there, and so on and so on. So these were the just to to let you know what our endeavors were in this field. These were our activities. So, I can conclude now with one sentence that I'm convinced that data analytics plays and will play an important role in the future of smart grid and in the future of microgrids and so on. We have dealt with two main areas, and it was power load forecasting and microgrid optimization. And in power load, the main aspect, I would say, is significantly lowering costs. And we have used a wide range of approaches, as you have seen, single versus ensemble models, blind versus adaptive models, batch, incremental, online, and so on, clustering. And in microgrid optimizations, there are some plans also for better energy utilization, new way of microgrid planning, the endeavors to maximize self-sufficiency, and I presented just some apps to support consumers, utility apps. Thank you very much.